Hello and welcome to the Bell Geospace podcast. I am Hillary Kennedy. Thanks for checking out this episode of the show. On today's program, we're going to be diving into gradiometry exploration and data acquisition. And joining me for the episode is Alan Morgan. He is the lead geophysicist at Bell Geo, and he's a subject matter expert in potential fields and has been involved with integrated interpretation of potential field data since 2004. And his global experience varies from mega-regional to prospect-scale projects, primarily in areas where seismic imaging falls short in efforts to assess geometry risk. He also specializes in 2D and 3D inversion and magnetic depth methods. So that is quite a resume, quite a mouthful. Alan, thank you so much for joining me.
Thank you, Hillary.
All right, so let's start off by bringing the heat in the form of geothermal energy. It's rapidly taking the place of oil and gas alongside some other sources of renewable energy. So can you explain how and why full tensor gravity gradiometry will find the original heat source in the geology?
Well, full tensor gradiometry, it detects density contrast, and there are many sources of density contrast that we expect in the specific geologic setting. These examples of density contrast can include compaction, changes in lithology, changes in mineralogy, mineral alteration, and offsets from faulting. So in each geothermal play type, we expect the heat source to produce some quantifiable density contrast with respect to the host rock that it's set in, whether that be a magmatic source, which is either active or extinct, an extensional domain source where we determine the basin thickness, or a conductive source where we map the formations or structures that are wicking the heat from depth. So prior to proposing a survey, we'll plug in the expected values of density contrast along with the expected depths of which we're finding the target and produce a forward model of the expected signal so that we can plan the proper line spacing and line lengths in order to capture the signal that we expect the target to produce.
Got it. So, as much of the oil and gas industry is reapplying its knowledge of oil exploration to the newer need for geothermal operations, before we dive into the topic all that more deeply, can you briefly clarify gradiometry compared to gravity and some more of the benefits?
Sure. Well, traditional gravity, its acquisition only measures the downward or Z component of the potential field. Full tensor gradiometry measures the tensor components, which are in each direction, X, Y, and Z, resulting in a mesh of components that exhibit directional sensitivity that is not obtained by single component measurement. So FTG is measuring the 3D effect of gravity in every direction. Benefits of the 3D measurement is an increase in resolution, which results in having to fly less densely spaced lines in order to achieve the required resolution when it's compared to single component gravity. So you don't have to spend as much money to get there. Additionally, the 3D tensor acquisition gives us the ability to perform many more edge detection algorithms, such as curvature or lineament extraction, and that increases confidence in the geometry of an interpreted structural framework, which is key to assessing geothermal plays.
Well, so, you touched on this a little bit, but data acquisition techniques used for gravity gradiometry exploration, they're good for the areas that can be tricky to acquire intelligent information. Otherwise, meaning, FTG excels in things like challenging terrain, remote areas, urban settings. Explain a little bit more about why that is.
Well, we fly our surveys as low as 80 meters above the terrain clearance when safety permits. And in challenging terrains, such as mountainous areas or in urban settings, the clearance is adjusted to safely navigate above such areas while still acquiring quality data. Our surveys can be flown as quickly as weather permits, and many surveys are completed within a few days to a few weeks of arrival on the field. And that depends on the size of the survey, and we're flying some quite large surveys recently. Our surveys often only require a single permit, and to begin operations, that's pretty quick. Ground acquisition, sometimes you have to obtain many permits, depend on who is in control of the property, and some may or may not be granted. So we have the advantage of getting a single permit before we usually even mobilize, and we're able to fly the survey without many complications.
Boy, that's nice. That's helpful. Nice and quick. Well, so let's talk a little bit about shallow areas like the top 500 meters of the subsurface. It's vital for geothermal, but as an industry, the importance of understanding it seems to be overlooked. So tell me about how FTG works in the shallow sections and why that is actually so important.
So full tensor gradiometry excels in identifying density contrast closer to the source. And the closer to the source, the better the signal. So, and the top 500 meters, it's a significant challenge for seismic reflection methods, as they're often weathering surfaces or unconformities or complex structures that scatter reflection waves. That's in close proximity to the source and the receivers, it makes it very complicated for seismic imagers to process that. They will often use what are called static corrections to sweep this under the rug and produce a cleaner signal with depth. So that a lot of times that top few hundred meters of a seismic reflection profile is often a smoothed product that is designed to clean up the signal more than actually quantify what is actually there. And the full tensor gradiometry, it's going to detect basically anything between the plane, the terrain, and what is below that. So we have algorithms set to actually correct for the terrain surface. And what we're actually trying to pick up is anything that is produced from geology, which is from the terrain down. Full tensor gradiometry has been utilized to help address the issue with seismic processing with promising results, as the density contrast that we measure does directly correlate to the interval velocities that are used in time depth conversions for seismic data. So it can be integrated with seismic measurements or seismic reflection measurements to improve their product as well. And anytime you have a more correct model, it helps make better decisions. And with respect to geothermal assets, the top 500 meters contains many of the anomalies we expect to see that are related to either alteration or shallow faulting.
Well, that's nice. That does sound promising. It's nice to have that and be able to get that data. So what are some ways that gradiometry helps of operators avoid any risks of induced seismicity, like accidentally causing earthquakes from pumping water into an earth's fracture?
The leading cause of induced or triggered seismicity is injection of fluids under pressure into fault zones. And operators are often unaware of the fault zones prior to obtaining permits to drill or inject fluids. Government agencies in each area have established guidelines with regards to minimum distances from known faults that operators can inject fluid under pressure, but often they're reliant on existing data to make those decisions and to place wells. So there is a significant chance that some of these faults go under the radar due to lack of data to support their existence. And a robust interpretation of the tectonic framework that is necessary to avoid pressured injection into such sites. So integration of full tensor gradiometry along with seismic reflection data and any other data that can be added that helps detect these faults, it's key to identifying where these zones are so that you reduce the risk of pumping fluid into one of them.
Yeah, that's super helpful. Well, Alan, I want to talk a little bit about you because I have been told that you like to follow up Bell Geo surveys in person to validate identified targets, which has also included a trip to Indonesia, where you found a previously unmapped outcropping of igneous intrusive. So I've heard while you're out and about, you also like to look for petrified wood for fun, which I think is really, really cool. And so I've heard that in one of your wood expeditions, you found something that shaped some of your scientific theories regarding the mobilization of silica. So can you kind of share a little bit about that story and some of your theories?
So I'll start out with the Indonesia story. So one of our clients in Indonesia had some relevant questions regarding some of the shallow anomalies that we're seeing in our data set. This was on the island of Kalimantan along the edge of the Kute and Barito basins. And this anomaly manifested itself along the Kute basin portion of the survey, but it was not visible in the Barito side, which is, it was just a matter of a few kilometers to the south of the edge of the basin. You were no longer seeing that signal. Our data quality was the same on each side of the survey. So the client had a very relevant question that needed to be answered. What was going on to produce these anomalies? So I was able to book a flight to the island of Kalimantan I was actually in Jakarta at the time, so it's not very, it's a very short and inexpensive flight to get there. I was able to book a driver with a four-wheel drive vehicle and GPS and have access to 2 days in the field to go check this area out. It turned out the GPS was somewhat useless because it was based off of existing paved roads. So it worked in the little town of Palangkaraya where I was staying, but once you got outside the city, it was just a blank map.
Oh, no.
So it actually turned out that an odometer in kilometers and images, Google Earth images of the existing logging trails was actually more useful than GPS. Well, I was actually expecting a GPS that was giving us latitudes and longitudes, but it was really just a simplified GPS for car navigation.
Gotcha.
Well, anyway,
you were expecting something a little more high tech.
I was, but I was able to make do with what I had. So a compass, looking at odometer readings carefully and knowing where to turn was actually quite a bit more helpful to getting to where I needed to go, as some of these areas were actually 200 kilometers away from the nearest cell phone signal. So I was without data and with only available aerial imagery and an area, a marked set of turns of how far I needed to go along each stretch of road and where to turn and which way to go. And it was somewhat challenging when you start to go into the interior of Kalimantan.
That's some Indiana Jones stuff you had going on there, Alan.
Well, not exactly. There was a bit of translation necessary. I had to ask the driver basically what the closest route would be, or if he knew the area. But we were able to actually get to the areas where I needed to go to answer the questions that I needed to have answered. So on the first day, we were able to go to a small town that was along the border of the two basins. And I was able to see on the north side of where the Kute Basin was, there were actually, there was a difference in cementation. The sand grains were actually held together by a hematite or iron oxide type cementation, which basically prevented it weathering very easily. And this produced a signal because it was slightly higher density than the rest of the sand around it that we were actually picking up from our planes. While it's on the southern side of the basin or the survey area along the Burrito Basin, the sand you could pick it up and it would just fall apart in between your fingers. It was like a sugar sand. So it was not held together very well and produced a relatively weak anomaly. So that answered the primary question. And then on the second day, I had another day to investigate other areas. I went to check out a magnetic anomaly, which it looked like a bullseye on the map. So I said, why not? Let's check this out. So we prepared, and it took most of the day to actually get to the site. We actually had to make some adjustments because the aerial imagery was 30 years old, and most logging trails aren't used for 30 years. So we had to make some adjustments. And when we got within a kilometer of the site, I set out on foot to actually look at the road cut to see if there were any interesting changes in geology. I started noticing that what was once flat-lying geology or lightly tilted geology all of a sudden became steeply dipping. And as I approached the area, I was able to see a dark-looking stone outcrop. And I didn't think much of it because there are a lot of lignite or low-grade coals in the area. And seeing a darker colored rock really didn't trigger anything as far as something I should be looking for out of the ordinary. And maybe that's why this outcrop had not been previously described or mapped. But it stuck out like a sore thumb in our magnetic data. There was also a gravity gradiometry signal that wrapped around it. And upon approaching the site, I was able to see that there was a denuded or bare spot area extending into the jungle away from the road. And I was able to collect samples of this material to determine what type of igneous material it was. So that that to me was quite exciting to find something that had, even in the client's detailed surface geology map, had never been described. And it was a way to ground truth our data to prove the resolution is actually increased. This was actually a 1 kilometer line space survey area. And for this feature to be, I think I measured it at the maximum, the outcrop was about 250 meters away from the road. It was actually, it could be like an iceberg, there was more buried at depth, but for it to be able to pick up an anomaly that was not expected to be very large, I thought it was quite significant to be able to go out and touch it. So, additionally, I was able to pick up some samples of petrified wood also that showed a significant degree of silicification. And that's where the fossil wood material is actually replaced with silica. You might think of the type of silica that you see. Glass is a type of silica. Opal is a type of silica. And so are agates. Agates are basically a translucent type of silicon dioxide that it's used in jewelry. It's also used for decorative arts. But most petrified wood is really not highly silicified. And there are only a few areas, Indonesia being one of them, and there are some areas out in the Desert West in the Great Basin where you can find agatized or even opalized woods, where the wood is actually replaced with mineral silica. The reason I think this is important to geothermal energy or geothermal exploration is that silica is not normally soluble. This glass, if it were soluble, I wouldn't be drinking a glass of water out of a silicon dioxide glass. So it actually requires elevated temperatures and a change in chemistry towards the alkaline chemistry for the water to dissolve silica. So there are a few other areas where I've collected wood where, and I'll actually show you a piece of it right here. You might not think of it much, but if I show you my finger in front of it, and then I show you my finger behind it, you can somewhat see through it. So this is actually relatively transparent. The degree of silica replacement is actually quite significant. So there are a few areas in South Texas where I've also been researching types of geothermal plays where a deeper salt formation actually wicks heat from closer towards the basement and basically wicks it up towards the surface. And there are a number of wells that actually record 60 plus degrees Celsius water temperatures in the top 500 meters of the surface. So there are heating applications, low temperature heating applications such as aquaculture and agriculture, where this temperature can be taken advantage of. I've also heard in the Delaware Basin, there are salt deposits that can also be used that actually can use this low temperature geothermal to enrich the lithium content of the brine, and that can be actually utilized for battery industries. So what this has in common to the silica is an indicator that there is excess heat somewhere in the system that is able to help dissolve the silicon dioxide from a source, which in the area in southeast Texas is the Catahoula Formation, which contains volcanic ash. And it's able to mobilize the silica, and it basically replaces something with pore space like the porous petrified wood. So this piece did come from southeast of San Antonio in an area where there's geothermal activity, according to the Department of Energy's website. There are a certain number of wells that actually exist in the area that are indicating high geothermal potential for a conductive type play. So also in West Texas, I visited one of our survey sites, and lo and behold, there's a shallow formation, a caliche formation, and I was able to find common opal deposits. Opal it's a hydrated form of silica, but it still requires slightly elevated temperature to be able to mobilize the silica. So it was present there also. That actually, I've done an exhaustive literature review. I have not found any other indications that in the Delaware Basin that they've noted opal occurrences. So I have an actual sample here in my office. It's a little bit dirty, so I can provide an image of it later. But there was actual confirmed common opal in the caliche from the Delaware Basin where we flew a survey. And there's also, I can share an image with you later that you can post on alongside of this, where we actually picked up an anomaly over a well that had elevated temperatures in 52 meters, the top 50 meters of the sedimentary section. And there we picked up a gradiometry anomaly around it. And this was only a few kilometers away from where I collected the opal sample in the Delaware Basin. So I think there's potential. I think there's correlation. And there's enough people that are collecting petrified wood. If you could compile the locations of where they're collecting the highest quality pieces, there could be more studies into what the correlation is between the geothermal gradient and the mobilization of silica.
That is a fascinating link. I love that you follow up on so many of your surveys in person because it gives you opportunities to develop these kinds of theories. That is really, really neat.
It's not possible everywhere, though. I try to get it more often than I'm allowed to. There are some areas where we fly surveys where it's just not possible. India is one of these areas where I've tried to gain access. They have some of the most interesting geology, especially along with the foreland basins of the Himalayas, what's called the Naga thrust. These are all areas where you have multiple plate boundaries colliding. They have their own areas of extreme geologic change, and it would make for a very interesting field trip. But however, safety first, we cannot just allow me to go everywhere without that being taken into account.
Right. Maybe one day.
I hope so.
Well, this has been so fascinating, Alan. Thank you so much. That is going to do it for this episode of Bell Geospace. And again, Alan, thanks for sharing your expertise and being here with me today.
Sure. Thank you.
Well, I want to thank all of our listeners for joining us too for this episode. We certainly appreciate it. And if you'd like to see more episodes of the podcast and stay up to date with future episodes, make sure to subscribe on Apple Podcasts or Spotify or wherever you listen to your podcasts. We'll be back soon with another episode. But until then, I'm your host, Hillary Kennedy. Thanks so much for listening.